Hello children, welcome back to another session of States of Matter. This is VKM. Welcome to Electron Chemistry Center. Hope you all are doing well. In this video, we will be continuing that States of Matter, the same topic. What is that? Gas laws. In the previous class, we had discussed about Charles' law as well as Boyle's law is completed. Now let us talk about another gas law we have, that is Avogadro's law. Avogadro's law. What this Avogadro's law states that Avogadro's law, for this both pressure and temperature must be kept at constant. So under similar conditions of temperature and pressure, both temperature and pressure must be kept constant. Equal volumes of all gases contains equal number of molecules. That indicates V is proportional to N. So V is equal to K into N, and V by N is equal to K. V stands for volume, N stands for number of molecules. See, let us say I have taken a container. Let us assume that it is a container of volume V, and it is also another container of volume V. Let us say it is having volume V, and it is also having volume V. In this, let us say ammonia gas I have taken. Let us assume that. In this also I have taken chlorine gas, Cl2 gas I have taken. NH3 gas, let us say it is of 1 mole. 17 grams is of 1 mole, and Cl2, that is Cl2 is of 71 grams. That is also 1 mole. And this is having Avogadro number of molecules, of course, and it is also Avogadro number of molecules only, because number of moles are same, number of molecules are same, volumes are same. Though the gases are different, but if moles are same, number of molecules are also going to be same, because 1 mole of any substance consists of Avogadro number of molecules. So that's why V is proportional to N. So for two different conditions, if I take it, V1 by N1 is equal to V2 by N2 can be taken. V1 by N1 is equal to V2 by N2, and it is the Avogadro's law. And obviously, if you draw the graph, because V is proportional to N, right? V is proportional to N, and if you draw the graph between volume and number of moles or number of molecules, you will get straight line passing through origin. Because V is equal to Kn, that is Y is equal to Mx form. So straight line passing through the origin can be obtained. Now another gas law, fourth gas law we have, that is Gay-Lussac's law. Fourth one we have Gay-Lussac's law. In stoichiometry, we had discussed about law of combining volumes. Do you remember? That is also a part of Gay-Lussac's law. But here we are going to keep volume as constant. At constant volume, pressure is directly proportional to temperature. That indicates P is equal to K into T, where K is the proportionality constant. Then P by T is equal to K. So two different conditions if I take it, then P1 upon T1 is equal to P2 upon T2. Same like V by T is equal to constant, such a way. And if you draw the graph between pressure and temperature, but volume is constant, right? pressure and temperature. But we are going to take volume is constant. In that case, here also pressure and temperature directly proportional, and here also you will get a straight line passing through the origin. Of course, line is has become little thick just to make a difference. That's all. Pressure is directly proportional to temperature. You will get a straight line passing through the origin, and these kind of graphs are said to be isochores. These are called as isochores because we have drawn this graph at constant volume. See, volume is constant in this. So the graph, whatever we get it at constant volume, are said to be isochores. Now we have fifth one, that is called combined gas law. Fifth one we have combined gas law. Combined gas law, sometimes it is also called as second Charles law. Sometimes it is also said to be Charles law 2. Actually, combined gas law, it's a combination of both combination of both Boyle's law and Charles law. Combination of both Boyle's law and Charles law. This is actually said to be combined gas law. We are aware of it, Boyle's law, that is volume is inversely proportional to pressure. Consider it as equation number 1. And volume is proportional to temperature. It is Charles law. And combine these equations, so V is proportional to P by T. Right, sorry, and V is proportional to, temperature directly proportional to T by P, and V is equal to K into T by P, and PV is equal to, obviously PV is equal to what we are going to get it. This is PV by T is equal to constant. This is the equation can be given for combined gas law, but different conditions are there. Let us assume if different conditions are there, then you will get P1 V1 upon T1 is equal to P2 V2 upon T2. It is very important. Combined gas law is very important. Based on that, we have different numericals. P1 is initial pressure, P2 final pressure, V1 is initial volume, V2 final volume, T1 is initial temperature, T2 is final temperature. So like that, we are done with 5 gas laws: Boyle's law, Charles law, Avogadro's law, Gay-Lussac's law, and a combined gas law. Let us talk about the most important concept of states of matter, that is ideal gas equation. Ideal gas equation, very important concept, of course. Ideal gas is that gas which obeys all the gas laws. As you are aware of it, no gas is ideal. All gases are not perfect because all gases may not obey all these gas laws under given conditions. In such cases, ideal gas does not actually exist. Practically, it does not exist. Theoretically, it can exist, but not practically. So, how do you derive this ideal gas equation? We have Boyle's law. Boyle's law, that is V is inversely proportional to pressure. In a similar way, Charles law can be taken as V is proportional to temperature. Avogadro's law, that is V is proportional to N. It is equation number 1, and it is equation number 2, and it is equation number 3. Take all of these 3 equations. Then from all of these 3 equations, you will get V is proportional to NT upon P. Then V is equal to, if you remove the proportionality symbol, place a constant. That constant is RNT by P. R is a constant. I can write it as PV is equal to nRT. PV is equal to nRT, where this R is called as universal gas constant. But proportionality constant, we are calling it as universal gas constant, and also known as ideal gas constant. Also known as ideal gas constant. If any gas obeys this equation. This is called ideal gas equation, of course. Any gas obeys this equation, that gas is considered to be as ideal gas. PV is equal to nRT equation, it should obey. And let us take that PV is equal to nRT. There are various forms of this equation. We are aware of it. PV is equal to number of moles is nothing but given mass by molar mass into RT, isn't it? So P is equal to mRT upon M into V. But you are well known about this mass upon volume. This mass upon volume can be replaced as density. So P is equal to dRT by M. It's dRT upon M, but whereas M is molar mass, D is the density. So D is equal to PM by RT. PM by RT. From this relation, you can understand density is directly proportional to pressure and density is inversely proportional to the temperature. Got it? Because molar mass of a gas is constant. For a particular gas, molar mass is constant, whereas R is constant and D is proportional to P and inversely proportional to T. That is, I can take it as D is proportional to P upon T. Or else I can take dt upon P is equal to constant. Dt upon P is also a constant. This I can take it as d1 t1 upon p1 is equal to, for two different conditions, d1 t1 upon p1 is equal to d2 t2 upon p2. This is the equation can be taken. For suppose if they have given two pressure conditions, two temperature conditions, like two density conditions, in such cases it is applicable. And based on this also we have numericals to solve it. But the point here, we need to talk about R, that is ideal gas equation, in that R is there. So PV is equal to nRT. R is equal to PV upon NT, where P is the pressure. Pressure I can take it as atmosphere, volume I can take it as liter, N I can take it as number of moles, and temperature can be taken as Kelvin. I can write this unit of R, it is liter atmosphere, mole inverse, it's 1 upon mole, that's a mole inverse, 1 upon Kelvin, Kelvin inverse. And pressure is anyway 1 atm, and volume occupied by the 1 mole of a gas is 22.4 liter if it is 1 mole at STP conditions, so 273 Kelvin. So if you solve it, R value will be 0.0821 liter atmosphere mole inverse Kelvin inverse. 0.0821, but this for sake of calculation, simplified calculations, what is supposed to do, you better take it as 1 by 12. 1 by 12 is almost equal to 0.0821. But if you take pressure in bar, then pressure is in bar units, then it will be 0.083 liter bar. But liter I can take it as decimeter cube also if you want to. Bar mole inverse Kelvin inverse. In a similar way, product of pressure into volume. That means we are applying the force. Pressure for per unit area can be taken it as force, right? So whenever if you apply the force, actually the gas can displaces to up to certain volume. That's why it is nothing but force into displacement. So force into displacement, that PV is nothing but work. It's a product of PV work, product of pressure and volume. So work done, you know that it can be measured in joules or calories or erg. So R is equal to, there is another value, that is 8.314 joule Kelvin inverse mole inverse, or else R is equal to 8.314 into 10 raised to minus 3 kilojoule Kelvin inverse mole inverse can be taken. And or else I can take R is equal to 8.314, this is 8.314 into 10 raised to 7 erg Kelvin inverse mole inverse, because 1 joule is equal to 10 raised to 7 erg. Similarly, 1 calorie is equal to 4.18 joules, so R is equal to 1.987 calorie Kelvin inverse mole inverse. Approximately, for sake of simplification, we can write 2 calorie mole inverse Kelvin inverse. This I can write it as R is equal to 2 into 10 raised to minus 3 kilocalorie mole inverse Kelvin inverse. See, there are different values for R, and many of the times they will give it to you in the examinations. 8.314, I can write it as 25 upon 3. For sake of simple calculations, I can write it as 25 upon 3. Is that clear? So it's all about ideal gas equation, and we have given in detailed discussion about ideal gas equation, and we will be solving some questions also in the later sessions, of course. Hope you like the video, and for more and more videos, please subscribe to my channel Electron Chemistry Center. Right? If you like it, then please click the like button. Thanks for watching. Signing off.